This is Eric Andelin, Senior Workflow Specialist at SimActive, and you're joining us for the webinar, Mining Site Monitoring Using Drones. And with me, I have my guest, Tim Whiteside, Senior Research Scientist at the Government of Australia, Department of Climate Change, Energy, Environment, and Water. That's a big one to say. Tim, say hi.
Hi.
So, Tim, all that aside, big title there. Give us a little bit about what you do and your background and your part in that organization.
Okay. So I've got a long background in remote sensing, completed my PhD in object-based image analysis about 13 years ago. And I currently work within DCCEEW, as the acronym is now pronounced, in the Office of the Supervising Scientist. The OSS is the main role is to protect the environment, particularly in Northern Australia and the Alligator Rivers region, which is where the World Heritage listed Kakadu National Park lies, protect these areas from the impacts of uranium mining. My job specifically within that is to develop monitoring tools that enable us to monitor the progress of rehabilitation and revegetation of a lot of the mining areas that have been a lot of the mining areas within the park and surrounding areas as they are being done.
Very good. Very good. So before we get too far, I'd like to go over some of the topics that we're going to cover during this webinar. And we'll cover them loosely as we move through the discussion. But 1, flying a drone over a mining site. 2, vetting the resulting imagery and accuracy. 3, producing map-based products with correlated 3D. And 4, analyzing geospatial data to monitor the site itself. Again, I'm here in the States. SimActive is in Montreal, and when we talk scale and size, Australia is way bigger as far as their national parks and things like that.
Oh yeah, totally. I haven't got the exact size of Kakadu National Park, but it's I can probably dig that out. If we just pause for a tick,
I've looked at it. It's massive. I understand, and I would imagine the number of visitors is maybe a bit lower because of its remote location.
It is massive, and so 20,000 square kilometers. There you go.
Very big, and it happens to have the uranium mine within the boundaries. It's, if I remember right, it's one of the largest or the largest in Australia.
The mine within the park, when it was in full production, would have been the largest in Australia.
Yeah.
Did produce quite a large amount of uranium, which produced a large amount of energy.
Yep.
So there's quite a big one in Central Australia now that we don't deal with it. Also in and around the park, there's a lot of smaller legacy mines that were mined in the 60s and the 70s that we also have interest in. Yeah.
Okay. So as part of your work, you guys are using aircraft, drones, helicopters to monitor these locations?
Currently, at the moment, we're using mostly drones to monitor, to do the monitoring of them. Yep, the drones we use generally are just the typical DJI drones, so M300, and some Mavics as well. The sensors we have on those include the DJI P1 photogrammetric sensor. Also, we do run a Sony A7R4 as well. We've got some multispectral sensors as well, including Microsense 10-band dual, and we're currently trialing the AgroWing 14 band sensor as well, and we run all that stuff through Correlator 3D.
Great. So since you're running DJI systems, the actual mission planning and flying of the drones is fairly straightforward, especially since it can identify, for the most part, what sensor it's actually carrying, correct?
Yeah. So with the DJI specific sensors, that's pretty straightforward. With the non-DJI sensors, there's a little bit of tweaking on putting in the camera parameters in, but once you put the camera parameters in to the software, it works out flight lines,
perfect,
spacing, and the amount of overlap and flight speeds, etc.
Yeah, I would imagine that, for example, the Sony and the Mika Sense typically are flying at different flight patterns, things like that, because of the focal length of the actual sensors.
Yes. So the flight widths, the spacing between the flight lines is totally different. For Mika Sense is quite narrow because of the focal length's quite narrow. So
So
tend to get tighter.
Do you typically fly, say, LiDAR imagery and multispectral of the same location at the same time while you're out there?
Yep. Yeah. So we do also have some LiDAR units as well. We've previously used the NextCore RN50 unit, and now we've moved on to the Regal Minivux. Fantastic. But we usually in a specific mission, we will fly LiDAR, then we will fly an RGB and multi-spec afterwards.
Very good. So you may, after traveling out there, like you said, it's very remote, so the amount of time it takes you to get out there into the field, you may only get one or two areas flown in the course of a day.
Yes. So it's usually we'll schedule to go out over, because it takes 3 hours to drive out to most of our areas of interest. So we'll schedule, if we're doing more than multiple sites, we have to overnight. Yeah.
And then do you typically have control in these locations, or are you just using prior iterations of the mapping to kind of register the data sets?
Well, we do use ground control. So the ground control, a lot of the sites where you request the mine to put in permanent ground control points, so that we can enable that, which enables quite easily to do the multi-temporal analysis. But we also have a couple of sets of aero points which we take out as well, which are the portable ground control points,
right,
with GPS built into them. Yeah.
Very good.
So if we're going to a new site, or if we're going to a site within the park where you can't put permanent ground control points, then we'll take the portable ones.
Very good. So I would assume you guys have access to the areas that you need to get to, other than through, say, a gate key or a card or something like that? Or is it just so remote that you don't really worry about that?
A lot of areas we are readily accessible by, I suppose, four-wheel drive track. Yeah. We do have a couple of reference sites near the mine which don't have accessible tracks, and we actually access them by helicopter. So we load up all the drones, batteries, other equipment, lots of water and food, and just get dropped in an opening and trek to the site, or fly across to the site with the drone, map the site.
So logistics,
back up, hop in the chopper, and
yeah. So logistics wise, you guys have a lot to do, because not to mention being able to survive while you're out there.
Yep. Yeah, no, there was one time when we got dropped off and the helicopter didn't come up to pick us up because it got a warning light back at the aerodrome. And we were stuck out there for 3.5 hours waiting for them to fly in a new helicopter from a neighbouring town to come and pick us up.
And then I would imagine the things that you're dealing with out there while you're out there is obviously the heat, wind conditions, because I mean, you don't go out there if it's windy, too windy to fly. And then I'm sure you've got all kinds of critters out there that you guys have to worry about.
Yeah. So if we're collecting data during peak biomass time when everything's green and flush, temperatures can get up over mid 35 degrees Celsius, and the humidities are 60 to 70% humidity at that time of year. This time of year it's quite nice. It's about 30 degrees, about 25% humidity. It's quite, but at this time of year also the wind does get up a bit, but so we can get gusts over 30-40 k's an hour just in a nice day.
Right. Yeah. So with the drones you have, you're collecting either RTK or PPK type data. You've got ground control points. So vertical accuracy is a component of what you do. Are you guys doing? Are you doing like volumes out there as well, or is it just more about making sure that the data set that you're comparing to matches what was previous?
Yeah. So it's more to do. We do some work with gully erosion. So looking at whether we can detect gullies forming and the change in size of those gullies. Vertical and horizontal accuracy is pretty key for that. But a lot of the work we do is looking at multi-temporal analysis of vegetation over time. So in the natural environment, does it change in the natural environment? And then how can we use that information to inform rehabilitation so we can monitor rehabilitation over time? Yeah, so I've got a couple of slides on that, which we can.
Yeah.
All right. So we do a lot of multi-temporal comparisons of data. So this is just an example of looking at revegetation or the changes in revegetation over time. So we've got 2 dates here. So we can detect the changes between dates. So we can look at growth. You can see quite a number of the trees there have grown. Recruitment, we can see a bit of ground cover recruitment in there, and we can also do mortality. You can see there's a couple of shrubs there that are there in 2022 and they're not there in 2023. So we've got something like 7,000 differentially GPS plantings, which are the green dots, and each one of those has a health descriptor over time, and so we can pair these to that, and using the data that we have, the health scores that they do manually in the field, ascribing to each plant, and this is the location of all those plants. The yellow dots are the differentially GPS plant on the ground, and you can see that it matches up quite well with the data, and this data is only being geometrically corrected using the DJI's RTK system, so we haven't even used any ground control on this, and you can see how accurate it matches up. So that's quite handy.
Yeah, fantastic. Well, I mean, that's what we do in correlated 3D. So it's always impressive to see, especially when you're looking at areas like this where it's just vegetation. So it could easily be misconstrued.
Oh yeah. What else have we got here? And then so currently starting to use AI and deep learning techniques to assign species to the plants that we don't have the labels for, using the labeled plants as training data, and from that then we should be able to look at the growth dynamics over time, changes in plant size, per species, and also correlate those metrics to the manual observations. And once we've got that all established on this pit, then we will look to roll it out over other areas.
Very good. So the other areas might be somewhat within the vicinity, so you could maybe even use some of this training data on those as well.
So as more areas on the mine site come under rehabilitation, we'll be able to roll it out and keep it ongoing.
So I mean, this is clearly done outside of correlated 3D. We don't do the AI or anything like that.
This is all done with Python scripting within a Jupyter notebook.
Fantastic. So I guess the one thing that I would say we can talk about here as far as correlated 3D, one, as we mentioned before, the ability to create these orthomosaics that actually fall in the right location and are repeatable. And two, color balancing capabilities within the software that you can continuously go back and identify things properly. And then three, not only that, but the multispectral. So the ability to bring in the multispectral cameras in correlated 3D so that you can create these outputs as well.
So the good thing about correlated 3D is that you can readily align when you process each date's data sets and you have ground control or good RTK, then they pretty much fall on top of each other, which is really handy for multi-temporal stuff. Also, the color balancing means that the color of the objects of interest tend to be constant if you're capturing data at a similar time of day. Also, a good thing about Correlator is the way it handles trees. A lot of the other photogrammetric softwares tend to treat them as fuzzy, blurry objects that are a little bit twisted and whatever. Correlated 3D seems to treat them with a bit more respect. And they actually look like what they are in the original photos. SimActive are really helpful with our processing of the Mavic 3M multispectral data. There was a couple of issues where the sun sensor toggle switch on the processing wouldn't turn on, and also it wouldn't take in panels, the radiometric calibration panels. It wouldn't take them in. So after chatting to Vivian, he pretty much got the engineers straight onto it, and within a week it was functional Mavic 3M data. So that was a really good outcome.
Yeah, especially with drones, because there are so many of them out there. A, the technology is new, and B, we may not see the technology from a customer until later. So credit to the guys in the development side who they'll jump right on it and get a solution. So we're happy about that.
So this next slide is on a containment facility in the south of the park where there was a lot of old abandoned uranium mines. There was a bit of infrastructure left behind that was slightly radioactive, so it was buried in a pit at this site. And our main role down here my main role is to monitor the canopy cover over time of this site to ensure that it's not exposed and eroding down to the area where the nasty stuff is. And so quite an easy way to monitor the canopy cover is to assume that everything that is green is canopy. And so we can do that readily with RGB imagery by creating a triangular greenness index. Is the RGB surrogate of NDVI, I suppose. Looks very similar once it's done. And then thresholding that and creating a cover map. And so we can compare these over time and see how the cover or how it's performing.
Yeah. You're the scientist, I'm not. One thought I had was, and I know, again, in correlator 3D, it's not our goal to do some of these things. We know our limitations. The one thing I would think is that you could run a DSM and then create a DTM, saving the features that it extracted in creating the DTM, which would be everything above ground, which would also tell you probably what the trees are.
If we could detect all the trees in the DSM,
yeah,
that would be correct.
Yeah,
but we can't.
Sure.
Due to the wind and also the nature of the trees, which I described earlier, some of them don't actually get picked up in the DSM at all. In an ideal world with nice trees and no wind, we could probably use the photogrammetric point cloud for that, but it doesn't always happen for us. So that's why we've got LiDAR as well. So I've also just whacked in a slide here on different GCPs and whatever.
Oh, fantastic.
We talked about that earlier, but maybe you could, So we've got the arrow points there, and also that's an example of a permanent one set up on the mine site.
Great. Yep, those look very familiar. And then, like you said, with the multispectral, then you have to have. Do you have special panels for those as well for the light refraction?
Yeah. So what we've used is we use the MicroSense panel. We've got a radiometric calibration lab. So we've measured the MicroSense panel and pulled out the reflectance information so it fits with the Mavic 3M. So I can put in a photo of that as well in there.
So to kind of wrap things up, you typically you're using correlator 3D to extract your base information, from which then you can go and take it into different software packages to produce the more relevant outputs.
Yeah, so we tend to use a lot of open source softwares. So mostly within Python, we use quite a number of packages within that to do all the analysis, as opposed to using commercial-based GIS and other softwares. We seem to be able to develop better pipelines and.
Over here in the States, I'm a big proponent of using QGIS. It just tends to work well.
Agreed.
Are you using the automated workflows at all? Being that you're going out to the same sites quite often?
Yeah. So pretty much we use the standard automated workflow. There may be a couple of tweaks if we do a quick QA QC over the mosaic and there's something that we're not happy with, we might tweak a couple of things, but generally we'll use the standard workflow. It seems to work quite well. Even with multispectral stuff, it does work quite well once you've got the panel and whatever in there.
Right. And then I would guess maybe even you guys are using a bit of the command line rather than going through the user interface?
Not yet.
Okay.
We're still just using the user interface. It seems to be good, but no, I think we'll just stay with the user interface at the moment. Yeah.
Well, especially if you want to view the the results as they're being processed, because that's of importance, then certainly, I mean, that's why we have both options. So you're doing this project, and I imagine you go out and monitor it quite a bit.
So depending on the site, that pit one we showed, there's probably people going out flying that once every 2 months or so. Once the vegetation is a bit more established, we'll probably go out twice a year after the wet season. and then probably towards the end of the dry. So you got sort of two weather extremes there. So you can, so that means that you can pick up variation that may be seasonal, as well as, so plants will senesce off, but then they may come back. So if you're visiting the site every end of every dry season, but not visiting in the wet season, you might think it's all not going very well, but it always comes back at some stage during the rainy season. Yeah. With the reference sites around the mines, the natural savanna areas around, we'll probably only visit those once every 3 or 4 years. But yeah, so we've got sort of a monitoring schedule. So the revisitation time is quite frequent when the vegetation is new and beginning to grow, but as it gets older, the revisiting is less frequent.
So this one project keeps you guys pretty occupied.
Oh yeah, pretty much. Yeah.
Yep. Okay. And then I would assume you do other similar small ones around the area that.
Yeah.
Yep.
Yeah. So I've got in a couple of weeks, I've got to go out to another old mine site and do some LiDAR data mapping out there. And next week I've got to go to a couple of cattle stations and do some weed mapping. But anyway, that's a totally different thing.
Completely different thing. I'm sure you have plenty of different things to do, but well,
yeah.
I mean, it's a fantastic case study, a great story, and we're very happy to be a part of it, working with you guys. And again, I'd like to thank you for your time.
No worries. Thanks, Eric.
Very good. Since we were a little bit short on our presentation with Tim, I'd actually like to go through and run through a bit of a project with everyone so they can kind of see how we do things in correlated 3D with regard to some of the items that we talked about in the webinar. And to do that, let's open up a project. I have a demo data set here with a quarry in it. Let's take a quick look at it. Here we go. Okay, so you can see quarry area right here in this image on this project. I can actually turn off some of the reference data here so it makes it easier to see. So here we have a quarry in Switzerland that we're going to take a look at. As you can see, we've processed it, but we'll go over some of those steps. You can see we have ground control points. They're right here. And you can see them. They were used as checkpoints, I believe. Again, the way we would import ground control points, you can see we're in the AT module. So the way that we would import ground control points is just go here, import a set of ground control points, point it to the direction or the directory that it's in, let it know whether it is in the current projection, whether you want it to be a GCP or a checkpoint or what have you. And then again, in this case, we could, if we had multiple files of control points, we could bring them in additionally. But we do have them in. If we wanted to do a manual one, we can do it this way by just doing create GCP and then go within the photo area, select a photo identifiable point, and then you could measure that for a checkpoint or a ground control point as well. The AT has been done, so there's nothing we need to do here. We could see all the steps, so step 1 through 3, and we can actually look at the quality reports for that step. So we're going to pull up a quality report here, and we can see that the project, the location, image tie points. So we've got a total of 900 plus images. Our tie points, our quality assessment is excellent. The projection error in our pixels is way below a pixel, so that's good. The average number of tie points per image, 119, that's very good. As you can see, we did not use them as ground control points, just as checkpoints. And here they are. They're listed as checkpoints. Here's the average error, the RMSZ, projection error, and so forth. And we can then go down and look at how the bundle adjustment was performed. So unconstrained and RTK, PPK assisted. So This tells us why we use these as checkpoints rather than ground control points. They were confident in their result with the RTK PPK, so they're going to use these as checkpoints and validate their RTK PPK solution. If for some reason the RTK PPK solution was poor, they have ground control points. They could run this as full AT unconstrained and use those ground control points as their solution. Again, the big benefit of having ground control points is even if you have PPK or RTK, if it fails, you've always got ground control points, which will always get you a solution. So keep that in mind. Anyhow, here are some of the, the parameters, and it's just saying that Correlator 3 calibrated these in the RTK PPK assisted. They said they fixed XYZ. Omega, phi, and kappa are allowed to float. So those were done. And you can see, again, this is iteration number 3. So you're not going to see much change here. If we looked at the initial, you'd see this go from red to green. And then we can look at the image adjustments. Not much there. The only thing we would expect to see adjusted is the omega, phi, and kappa, and it was. And then we can see what it's done. It's calibrated the camera. So you can see some adjustments here. They're usually minor, that's all they are. But since it was done, when you're finished with the project, you could save out this calibration and reuse it. So just remember that. And here's the control point analysis. So we get into more in-depth detail on our control points. In this case, they're checkpoints. So we'll see, again, some information on the RMS XYZ error. And then we can get into even more detail and look at those checkpoints individually. So they call them verification points. What we're concerned about here is the Z, and it's pretty darn good. So I understand why they're happy with that. And then the last thing would be, just some information on the workstation that you were using when you calculated all this out. So again, here's our data set. We can turn off the imagery, so it's a little bit easier to see. We can, we'll go ahead and get out of AT. All right, and then I'm going to turn off the images again, get a better view of it. We'll turn off the mosaic and we'll look at the DSM. So the DSM is pretty sharp. You can tell that when it was created, they used a constraint file when they created the DSM, and that would be right here. So if we go to generate a DSM, it's going to ask you if you've got a constraint file to use, which is just a boundary file, which you can bring in, which is a shape file or anything like that. So that was done. And what it's doing is it's minimizing the amount of processing that the software has to go through. So obviously, if your area of interest is only a small area and you've got a large data set, then don't bother processing the large data set. You can minimize that by creating your boundary around your work area. So that's there. Obviously, the DTM was produced from that as well. And we can take a look at that. There's the DTM, nothing special there. What I would like to say is that in this conversation, we're talking about quarries and volumes. You're probably going to want to do your volumes from the DSM. And that's because, the job of creating the DTM is to eliminate features such as buildings, cars, trees, those kind of things. And we'll look at it and you can see they've been eliminated in these areas. You don't see those buildings anymore, anything like that. But we'll go back to the DSM. And again, we can see all of our information is still there. So when we're going to do a volume, it's going to be of, certain features within the quarry. And if we look at, for example, if we turn the mosaic back on and zoom in a little bit, we'll zoom into this area. You can see that maybe there's some stockpiles that they want to measure. And if they wanted to do that, you could create individual boundaries around these stockpiles and go ahead and do your volume measurement right here. And if we select this, for example, it'll bring up the volume measurement tools. So if I wanted to just draw a polygon boundary around this and say, give me a measurement, I could do that. I could also just do a rectangular area, I suppose, if I wanted to do that. More importantly, and the benefit of doing it here with Correlated 3D is that if you have a multiple stockpiles within this area that you need to monitor the volume of, and say you're doing that on a frequent basis, just like Tim is doing in his projects, if you need to come back and measure those so you know they're going to be static locations, you can always bring in a shapefile boundaries of those features. So if we do that, and I can open up the vector tree here, and we can look at the vector files that were brought in here. So I'll zoom out just a little bit so we can look at this. So here is a boundary file. It looks like if you're going to do just some work in the actual quarry area, that looks like that. What is actually, it's an exclusion zone. So what it's saying is if you're creating, for example, a DTM, but you don't want it to take features out of the area within the exclusion zone, it won't. And there's a reason for that, and we'll talk about that. But if we look at these others, you can see one called shape, and this one looks like it was set up to measure the volumes of these three stockpiles. And you can see they're highlighted there. Might be kind of hard to see. Let me turn off the mosaic so you can take a look at that. And there we go. There's the stockpiles. And if you know they're going to be there, and you want to make measurements of these, as time goes by, you can use these shapefiles or continuously use them once you reprocess this model, say a month later or 2 months later with new imagery. So we have that boundary there, and again, that is for the volumes. And let me zoom out a little bit again. And the reason why I want to do that is because I'm guessing that this crop shape file is, yes, it's actually the boundary of the project, of the quarry area. As I mentioned before, they created that. Therefore, all that extra work doesn't have to be done. And again, that's why that's there. So let's, again, go back in and look at how we would measure the volumes of these stockpiles. So we've got our shape highlighted, and again, I'll zoom back in here a little bit. We've got that area highlighted, and we have the volume tool selected. So again, we have our options here, and everything's good the way we want it. So what we're going to do is select volumes, measure and select volumes. And it's going to give us a handful of options here. So default is interpolate DEM at the polygon boundary. So that means it's just going to interpolate the surface underneath at that boundary, because nothing's always flat. There are chances that it'll be flat, but most likely that it's not. It's just laid on the earth above it. So that's going to do the interpolate. The other feature is interpolate polygon elevation. So it could just calculate an average elevation in here. You could type in a fixed elevation. So, for example, it's flat. You could type in a fixed elevation there. If it was laying, say, on concrete, you could just type in that fixed, or you could say use the fixed elevation. And then you have a couple other options here: remove constant offset, add constant offset, and then use a reference to EM. Maybe somebody's provided that for you. But we'll go with the default, and we will select process. And as you can see, a process is really fast. It doesn't take very long at all. And it's given us the information for all three of these stockpiles. So polygon 0, polygon 1, polygon 2. It gives you a volume cut, a volume fill, a terrain area, orthogonal area, and then the volume covered. So how much of it do we actually cover? And it's done that for each polygon. As you can see, polygon 0, polygon 1, polygon 2. And it's also giving you a total volume cut and fill. Now, this is great information, but we all know that your customer is going to want it in a certain format, in a certain way. You're probably going to provide that to maybe your surveyors or your engineers, and they've got a specific form that they're going to fill out with this information. So that said, what you can do is you can save and close this information, and when you save it, you're saving it as a text file in the project. So we'll just go here and we'll just call it volumes text. As you can see, this has been done before. We can hit save. Now we have that volume information in a text file, which then you can take out into, bring into Excel or whatever your end user is looking for. So that's how we would do volumes with relation to in a quarry situation. So again, not something that Tim was having to deal with because his mine site is actually a mine underground in the mine. So what you're going to see in his scenario is just a hole in the ground that people go in and out of, or equipment go in and out of, and they do all their work underneath, which, fantastic terrestrial LiDAR tools can get involved in that and go under the surface of the earth and calculate all that stuff, which is really cool. Not what we do, and not what Tim is doing with our software. What Tim is doing in his case is more so monitoring the vegetation and how those vegetation sites are reacting to the mine remediation. So that's the difference between the two, but I wanted to clarify that you can do volumes in Correlator 3D. You obviously, the way this one was set up, well done. They used RTK PPK, but they also had checkpoints, which they used to make sure that their RTK PPK solution was good. And we'll zoom in here and see if we can find some of these checkpoints. Yeah, here's one here. So we can see how it lays out. And it looks pretty good. So, I think the results of this project, the results of the volumes that came from this are going to be pretty darn accurate. So, there are always things to consider when you're measuring volumes, whether the stockpile is rock, whether it's, wood chips and things like that, which may, those things may compact over time. So you're going to see that volume change. So, that's not for us to do on our end with Correlator 3D. With Correlator 3D, we're all about building the surface, and from the surface, you can do those kind of measurements. And what we like to show here is that, there are a lot of products that you can get from ortho imagery, elevation models, and things like that. That, again, Tim was talking about AI and, using machine learning to extract out, maybe what type of vegetation that they're looking at, and how that vegetation, the size of that vegetation compares to what it, was previously or going forward in the future. And the way all that works is that you have a very good color balanced mosaic that is repeatable over time, that you can then do the AI and the machine learning on top of to get the information, in this case environmental information, out to the customers. In this case it was the government of Australia, as they monitor these things. But I think with that, I can wrap up this part of the webinar. Once again, I'd like to thank Tim Whiteside for joining us. I'd also like to thank you, the viewer, for attending. If you did leave a question, we will answer that question as soon as possible. Remember, this webinar, as well as all other webinars and our podcast, can be found on our website, www.simactive.com, under the Learning tab. Thanks again. Until next time.